continue our discussion on the solution of the one dimensional Schrodinger equation for a free particle. As we had discussed in our last lecture, the electron or the proton or the neutron is described by a wave function psi such that mod psi square dx is proportional to the probability of finding the electron between x and x plus dx. So, this is the mod psi square is the probability distribution function, and we can always normalize this wave function such that the integral from minus infinity to plus infinity is equal to 1. As we had discussed earlier, this is known as the normalization condition, and when this condition is satisfied, this quantity mod psi square dx represents the probability of finding the particle between x and x plus dx. This is the Max Born's interpretation of the wave function. Since this is the probability distribution function p of x dx, so therefore, if the electron or the proton is described by the wave function psi, then the expectation value of x, then the average value of x will be equal to integral from minus infinity to all limits, always all the integrals are from minus infinity to plus infinity, x mod psi square dx. So, this is the expectation value of x, and which is usually written like this, as we had mentioned earlier, minus infinity to plus infinity psi star x multiplied by x and psi of x dx. Similarly, the expectation value, this is the expectation value of x. Similarly, one can write down the expectation value of x square. So, x will be replaced by x square here. So, this will be psi star x x square dx. So, if I know the wave function psi of x, then in principle I can evaluate this integral and obtain expectation value of x square and the expectation value of x. If we determine this, then the uncertainty in x, we define this is equal to under root of the expectation value of x square minus expectation value of x whole square. So, this is the uncertainty in the measurement of the quantity x. Now, let us suppose that the initial wave function at time t equal to 0, the wave function describing the electron or the proton at time t equal to 0 is a Gaussian wave function, and I have a normalized Gaussian wave function like pi sigma 0 square raised to the power of 1 by 4 e to the power of minus x square by 2 sigma 0 square e to the power of I by h cross p naught x. So, the probability distribution at t equal to 0 is a Gaussian function. So, p of x dx, this is equal to mod psi x square dx, and this will be the square of this quantity pi sigma 0 square under the root, because the square of this is under the root, and then the modulus square of this is 1. So, this is e to the power of minus x square by sigma naught square. So, in order to find the expectation value of x or x square, I just have to substitute this quantity in this here and carry out the integration to evaluate x, expectation value of x and expectation value of x square. So, therefore, we can evaluate, if we do that, then we obtain that the expectation value of x is equal to from integral minus infinity to plus infinity x times p of x dx. So, this will be 1 over under root of pi sigma 0 square x into e to the power of minus x square by sigma naught square dx. And as you can see, this is an odd integrand. So, therefore, this implies that x is 0, the expectation value of x is 0. So, that if you make a large number of observation of the position, x coordinate of the position of the particle, then and you take the average of these over a large number of measurements, you will get the value 0. Sometimes you will get plus something, sometimes you will get minus something, but the average of that will be 0. Now, the expectation value of x square will be just, if you put x square, then this integral can be easily worked out in terms of gamma function, because this will be equal to 2 times under root of pi sigma 0 square integral 0 to infinity x square e to the power of minus x square by sigma naught square dx. You can now substitute x square by sigma naught square equal to y and then carry out the integration. It is a very straightforward integration, and the final result will come out to be sigma 0 square by 2. So, therefore, the delta x, the spread in the value of x, is equal to x square minus x average whole square under the root. This quantity we have shown this to be 0. This quantity is sigma 0 square by 2. So, we obtain that for the Gaussian wave packet, this becomes sigma 0 by root 2. This is the uncertainty in the measurement of x. This is the uncertainty. The electron is described by a wave packet. So, at t equal to 0, it is somewhere located in this region. So, therefore, the average value, so this is the origin, the average value is 0, but there is a spread in the wave function, as I had shown you earlier, and this spread in the wave function is described by the uncertainty delta x, and that is equal to sigma 0 by root 2. So, this result we have obtained, that delta x is equal to sigma 0 by root 2. So, this is an important result for a Gaussian wave function. We next calculate the expectation value of the momentum operator and the expectation value and the uncertainty in the momentum. Now, as we had discussed earlier, that this general solution of the Schrodinger equation is given by one dimensional Schrodinger equation is actually a wave packet 1 over under root of 2 pi h cross minus infinity to plus infinity a of p e to the power of I by h cross p x minus p square by 2 m t into dp. So, at t equal to 0, psi of x comma 0, this will be, I substitute t equal to 0. So, I obtain under root of 2 pi h cross minus infinity to plus infinity a of p e to the power of I by h cross p x dp. Thus, this psi of x 0 is the Fourier transform of a of p, and conversely the Fourier transform of a of p, the inverse Fourier transform, will be given by, as we had discussed earlier, this is the inverse Fourier transform 1 over 2 pi h cross psi of x 0 x comma 0, and now it will be have a minus sign minus I by h cross p x dx. So, if I know psi of x comma 0, the recipe is this, as we had discussed earlier, the recipe is this. If I know psi of x comma 0, I can calculate a of p. Once I calculate a of p, I substitute it in this equation, carry out this integration and obtain psi of x of t. That will describe the evolution of the wave packet with time. So, we have assumed that psi of x comma 0, we had said that this quantity we assume to be this equal to 1 over under root pi sigma 0 square raised to the power of 1 by 4 e to the power of minus x square by 2 sigma 0 square e to the power of I by h cross p naught x. So, if I substitute this expression for psi of x comma 0, I can carry out the integration using that integral e to the power of minus alpha x square plus beta x. It is a very straightforward integration, and if you do that, you will obtain the following expression for a of p, and you will obtain a of p is equal to sigma 0 square plus pi. Please work this out, pi h cross square raised to the power of 1 by 4, and the Fourier transform of a Gaussian is a Gaussian minus p naught whole square sigma naught square divided by 2 h cross square. So, this function, the wave function is Gaussian, its Fourier transform is also a Gaussian, and if you plot this, you will find that the Fourier transform, that the a of p function is peaked around p equal to p naught, and with a spread which is of the order of h cross by sigma naught. Then, so this is the Fourier transform function. So, then if I want to measure the x component, the momentum, or just we say that the p, and the average value of momentum, we had discussed this. So, the average value of momentum will be equal to minus infinity to plus infinity psi star p psi dx. So, p psi will be equal to, we have to replace this by its operator, we had discussed this in detail. So, minus infinity to plus infinity psi star minus I h cross, I can put a bracket here, delta psi by delta x dx. And if you carry out, if you substitute for psi this particular expression, and you carry out this integration, then you will find that this will come out to be minus infinity to plus infinity p of mod a p square dp. Therefore, we can interpret that a of p mod square dp is the probability of finding the momentum between p and p plus dp. And from Parseval's theorem, if psi square is normalized, then this is also normalized, that is minus infinity to plus infinity a of p square mod p square dp is equal to 1. If the wave function is normalized, then its Fourier transform is also normalized. So, this is the expectation value of p. Similarly, you can calculate the expectation value of p square. For p square, this will be a p square here, and so this will be minus h cross square delta 2 by delta x square. And if you did the algebra once again as we had done earlier, so this will come to be p square a of p mod square dp. We do have the expression for a of p. So, a of p, as we had derived it a few minutes back, sigma 0 square by pi h cross square raised to the power of 1 by 4 e to the power of minus p naught whole square sigma naught square by 2 h cross square. So, all that I have to do is, therefore, I have the expression for a of p, an analytical expression. A of p square will be square of that. I substitute it here, multiply by p square and carry out the integration. That will give me p square, and for p I just have to multiply by p and carry out the integration. The algebra is slightly involved, but it involves simple evaluation of the integral. So, one finds with a little bit of algebra. I would request all of you to carry out this algebra. So, after a bit of algebra, which is just evaluation of the integrals, we will obtain that the expectation value of p, that the average value of the x component of the momentum is p 0, and the expectation value of p square will come out to be p 0 square plus h cross square by 2 sigma 0 square. I would request all of you to work this out. It is a very straightforward algebra, but one must do that. So, therefore, delta p is p square average minus p average square. So, p average square will be p naught square. So, if you subtract this from this, the p naught square cancel out. So, delta p will come out to be, if you find out delta p, that will be equal to, delta p will be equal to under root of p square minus p average square. So, this will be h cross square by 2 sigma naught square. So, we obtain finally the following expressions for delta p and delta x. Delta p we have just found out that this will be equal to h cross by root 2 sigma naught. Delta x we had found out to be equal to sigma naught by root 2. So, therefore, the uncertainty product, this is known as the uncertainty product delta x, delta p, the sigma 0 cancel out, this will become to be, and this is typical of a Gaussian wave packet. The Gaussian wave packet corresponds to the minimum uncertainty product. So, we obtain this. Now, this is actually the uncertainty product is minimum, and one can show this analytically, because you may recall that when we had derived the uncertainty principle, we had first proved the Schwarz's inequality, and the inequality was mod f square d tau times mod g square d tau. This was greater than or equal to quarter of integral f star g plus f g star d tau and whole square. Now, I can easily show that if g is a multiple of f, that is, let us suppose g can be complex, but let us suppose it is a multiple of f, but for the time being we can assume that alpha is a real number, let us suppose. So, this becomes f square and this g square. So, g star, so mod g square becomes alpha square mod f square, where alpha is a constant and I am assuming this to be a real constant. So, alpha square. So, the left hand side becomes alpha square, and this also becomes f square d tau, this also becomes f square d tau. So, you will have integral mod f square d tau whole square. On the other hand, this quantity f star g will be equal to, this will be equal to alpha mod f square, This will be also alpha mod f square. So, the sum of the two will be 2 alpha mod f square, and if I square this, it will be 4 alpha square mod f square d tau whole square. The 4 will cancel out with 4. So, the right hand side will also be equal to alpha square mod f square d tau whole square. What I have done is the following. I had proved earlier that this inequality is always valid. I have just now shown that if G is a multiple of f, and let this multiplicative constant be real, then the left hand side and the right hand side become equal. So that this inequality becomes an equality. So therefore, using this inequality, we had proved that delta x, delta p x is greater than or equal to half h cross. And we had assumed that f was equal to p psi, which is equal to minus I h cross, say d psi by dx, and we assume that G was equal to I x psi. So, if G is a multiple of f, then you will have this. If I assume that G is a multiple of f or f is a multiple of G, does not matter either way. So, then this tells us that I x psi will be equal to minus I h cross alpha d psi by dx. So, the I on both sides cancel out, and if I take psi in the denominator, then I will obtain 1 over psi d psi by dx is equal to minus h cross alpha, and let me put it as x by sigma naught square, just where sigma naught square is just h cross alpha. So, if I integrate this out, so this becomes log psi. So, psi becomes equal to e to the power of minus x square by 2 sigma 0 square. So, when the wave function is Gaussian, G is a multiple of f, and so therefore, the inequality becomes an equality. So, that for a Gaussian wave function, delta x, delta p becomes equal to half h cross. Okay. Finally, now we had shown, so this is the uncertainty product. Finally, we have that the wave function, I want to study the time evolution, that how I had shown you a diagram, but maybe we will show this again today, time evolution of the wave function. So, that is given by psi of x t is equal to under root of 2 pi h cross, integral, the limits are from minus infinity to plus infinity, e to the power of I by h cross p x minus p square by 2 m t dp minus infinity. So, if I know psi of x comma 0, I know a of p, and in fact, for the Gaussian wave packet, we had shown that a of p is equal to sigma 0 square by pi h cross square raised to the power of 1 by 4. It was a Gaussian momentum distribution minus p naught whole square sigma naught square by 2 h cross square. So, I know the function a of p, I substitute it here and carry out the integration of p over p. Once again it is a slightly cumbersome integral, but you just have to repeatedly use, you just have to again use the integral that we had written down the first day, alpha x square plus beta x dx from minus infinity to plus infinity. This is equal to square root of pi by alpha e to the power of beta square by 4 alpha. If you do that, you obtain an analytical expression for psi of x comma t, and if you take the modulus of that, then you will get psi of x comma t mod square. This is equal to under root of pi sigma square as a function of time e to the power of minus x minus p naught over m into t whole square divided by sigma square of t, where sigma of t after carrying out the integration you can show comes out to be sigma naught 1 plus h cross square by m square sigma 04 into t square raised to the power of half. So, there are two very important points in this formula. The first point is that the center of the wave packet is moving with a velocity p 0 by m. This is the group velocity of the wave packet. The whole wave packet moves with a certain velocity, the average velocity, the group velocity, and that group velocity of the wave packet is given by p 0 by m. And the second important point is that the width of the packet is increasing with time. So, that initially the packet was the real part of the wave function was something like this. At a later time it would have expanded, and it, as I will show you, the whole thing expands. The delta x increases. In fact, if you use this wave function and evaluate x, which is equal to mod psi x comma t whole square into x dx from minus infinity to plus infinity. If you first evaluate mod x, expectation value of x, and then you evaluate mod x square, then you will find that the uncertainty in x will come out to be equal to sigma naught by under root of 2 into under root of 1 plus h cross square by m square sigma naught 4 t square. That is, the packet expands, and the packet expands because of the dispersion relation, that omega, that you see you have here E is equal to h cross omega, and you have also E is equal to p square by 2 m. So, h cross omega is equal to p square by 2, that is h cross square k square by 2 m. So, your omega is equal to h cross by 2 m times k square. So, you have a nonlinear relationship. If omega is proportional to k, as it is indeed true for electromagnetic waves in free space, there is no broadening of the pulse. But if there is dispersion, what is dispersion? When omega and k has a nonlinear relationship, then there is a broadening of the pulse. So, the broadening of the pulse is because is a manifestation of the fact that we have a dispersive medium in which omega k relationship is not linear. So, delta x is so much, the delta p remains the same. The delta p is equal to h cross by under root of 2, that does not change with time. H cross by under root 2, what was the expression for h cross by under root 2 into sigma naught divided by sigma naught. This does not change with time. So, that the uncertainty product will change with time, and you will have delta x delta p will be equal to h cross by 2 1 plus h cross square by m square sigma naught 4 into t square. So, this is the uncertainty product for a propagating Gaussian beam. The beam expands along the x direction, along the direction of propagation of the wave. So, we have done all the algebra. Let me just quickly go through my slides, which will tell you the same thing. So, we continue with our discussion with the free particle. This is the, as you may recall, this is the one dimensional Schrodinger equation for a free particle. We had discussed the general solution of that. So, the general solution of this equation is given by this equation. This equation describes the propagation of a wave packet. So, how do we study the evolution of the wave packet? So, I put t equal to 0. So, then this term becomes 0. So, this becomes a p e to the power of I by h cross p x. So, the recipe is that I find out a of p by taking the inverse Fourier transform, and if I take the a of p by taking the inverse Fourier transform and I substitute it in this equation, and I will get psi of x comma t. So, in a Gaussian wave packet, this is the form of the wave function that is given to us. So, my problem is that if I know the wave function at t equal to 0, what is the wave function at a later time t? In order to do that, we first showed that the expectation value of x is 0, then we showed that the expectation value of x square is sigma 0 square by 2. So, therefore, this is 0. So, the expectation value of x at time t equal to 0, is sigma 0 by root 2. Then, in order to study the evolution of the wave packet, we calculated the a of p, the momentum distribution function. So, that is the inverse Fourier transform of psi of x comma 0. If I substitute this here and carry out the straightforward integration, I will obtain this equation, which is also a Gaussian, but peaked around p equal to p 0. And therefore, we can interpret mod psi of x d square dx as the probability of finding the particle between x and x plus dx, and a of p mod square dp is the probability of finding the x component of the momentum. Of course, we are considering the one dimensional case, or the x component of the momentum between p and p plus dp. So, since a of p is given by this, I can then calculate the expectation value of p. If I would request all of you to carry out this integration, and if I multiply the square of this function with p and carry out this straightforward integration, this is the average momentum. This is the average momentum with which the wave packet moves. And similarly, you can calculate p square. So, you do this and you obtain this. So, delta p, which does not change with time, becomes h cross by root 2 sigma naught. So, at time t equal to 0, delta p is so much, delta x is so much. So, delta x delta p is the minimum uncertainty product, and that we had discussed earlier. So, how do we find the evolution of the wave packet? As I said earlier, that the psi of x t is given by this, and if psi of x comma 0 is known, then I can find out a of p by taking the inverse Fourier transform. So, I have been able to find the a of p. I substitute it here and carry out the integration. And once again, the integration is not very straightforward, is little cumbersome, but it is very straightforward. If you do that, you will find that mod psi of x t square is equal to 1 over root 2 pi 1 root pi sigma of t, and the wave packet itself moves with the center of the wave packet moves with the velocity p 0 by m. This is the group velocity of the wave packet, and the width of the Gaussian pulse increases with time, So, you will have this wave function. So, x is so much. So, delta x actually increases with time, because the sigma of t increases with time. So, therefore, the uncertainty product increases with time. At t equal to 0, it is the minimum. So, this is my localized wave packet. The electron is described by this wave packet. It is localized somewhere here, somewhere between the here. The localization is within a distance of the order of sigma naught, and the corresponding momentum distribution is of the order of h cross by delta x. So, that the uncertainty product is satisfied. Now, this is what I had shown earlier also. So, this is the evolution of the wave packet, and let me do it very carefully. So, the wave packet, the electron is just, let me do it more slowly. So, let us suppose we put it 500 here, and so the electron is described by this wave function. So, if you ask me the question, is the electron a particle or a wave? The answer is, it is neither. It is described by a wave function. So, it is somewhere localized where the wave function is finite. You can tell, you can predict a probability distribution of finding the electron as it evolves with time. And so, therefore, there is an uncertainty in the measurement of x, there is an uncertainty in the measurement of p, and that is contained in my uncertainty in the solution of the Schrodinger equation. So, therefore, Schrodinger equation itself contains uncertainty principle. So, you see, I have here the electron is described by this wave function, actually it is the real part of the wave function. So, it is somewhere localized here, and the packet itself broadens with time, and that is because of dispersion. So, therefore, to summarize, an electron or a proton or a neutron is neither a particle nor a wave. It is described by the wave function. A free particle, let us suppose the propagation is only in the x direction, and I neglect the y and z variation. It is described by a wave packet. So, when the electron leaves the filament, it is described by a localized wave packet, which moves with a velocity equal to p 0 by m. So, the packet itself moves forward, it is localized somewhere there, and the localization is consistent with the uncertainty principle. So, that is what my quantum mechanics tells me, that the electron or the proton or the neutron is neither a particle nor a wave. It is described by the wave function, by a wave function psi, which is a solution of the Schrodinger equation. Now, let me consider a slightly more difficult problem, not difficult, little more involved problem, that I have a Gaussian wave packet which is propagating in the x direction. This is my x direction, and then it has a slit of width b in the y direction. So, I am neglecting z. So, a packet is moving in the x direction, but constricted in the y direction. So, the wave packet here is a Gaussian wave packet. So, I have here therefore, a wave function psi of x comma y comma 0 at time t equal to 0. First, the x part at time t equal to 0 is a pi sigma 0 square raised to the power of 1 by 4 e to the power of minus x square by 2 sigma naught square e to the power of I by h cross p naught x. So, this is a Gaussian wave packet just similar to the one that we had considered, localized within a distance of sigma naught and propagating in the x direction. But I now multiply by a function y, function of y, which is such that psi b of y is equal to 1 over under root of y, 1 over under root of b, I am sorry, for y less than b by 2 and minus b by 2 and 0 everywhere else. So, I allow this the wave function to be finite only in this region and 0 everywhere else. This is my y axis. So, it is a Gaussian wave packet encounters a slit of width b. Now, this wave function is normalized, that is minus infinity to plus infinity mod psi b of y mod square dy. This is equal to 1 over b from minus b by 2 to plus b by 2. This is psi b y square is 1 over root b. So, that the square of that is 1 over b multiplied by dy. So, this is b by 2 minus b by 2. So, that is b by b. So, this is 1. So, it is normalized in the x direction and also in the y direction. So, I want to study the evolution of this wave packet. So, then what I do is, instead of taking a one dimensional Fourier transform, I take a two dimensional Fourier transform. So, we write this down as that psi of x comma y comma 0 is equal to 1 over root 2 pi h cross whole square, then integral a of p x comma p y e to the power of I by h cross p x x plus p y y dpx dpy. So, therefore, in order to determine a p x y, I take the two dimensional Fourier transform of psi of x y. So, I get a p x comma p y is equal to 1 over under root of 2 pi h cross whole square, and then the integral, first integral over x multiplied by e to the power of minus I by h cross p x x, and then there is a second integral, that is psi b of y e to the power of minus I by h cross p y y dy. This is the Gaussian wave packet that we had written down, that this quantity we will substitute here, and this quantity is 1 over root 2b. So, this is also from minus infinity to plus infinity, and this is also minus infinity to plus infinity. The x part integral will come out to be the same thing. So, some factors into e to the power of p minus p naught whole square sigma naught square by 2h cross square. So, that is the integral that just similar to one that we had found out earlier. So, actually I can write down a p of x comma p y. So, this is a product function a p x and a p y. Actually, this should be a p x, and a p y will be the integral of that. So, let me evaluate this. So, a p y is equal to one factor I will take here 2 pi h cross. Please see this, is very, it will give me a very important result, psi b of y p y y dy. But this is 0 for y greater than mod b by 2. So, therefore, this comes out to be 1 over under root of 2 pi h cross 1 over under root of b, and then from minus b by 2 to plus b by 2. Let me put this as e to the power of minus alpha y, where alpha is equal to p y by h cross. The integration of this is very straightforward. That is, the integration will be, you just have to integrate this and you will find e to the power of minus I alpha y divided by minus I alpha from minus b by 2 to plus b by 2. All right. So, this will become, if I do it like this, so this will become e to the power of minus I alpha b by 2 minus e to the power of plus I alpha b by 2 divided by minus I alpha. So, there is a minus sign sitting in the denominator. I put it plus sign here and minus sign here, multiplied by 2 here and multiplied by 2 here. So, this becomes 2 by 2 alpha, 2 by alpha, this becomes 2 by alpha, and this will be e to the power of I alpha b by 2 minus e to the power of minus I alpha b by 2 divided by alpha, divided by 2i. So, that will be sine of alpha b by 2. So, this is equal to this is equal to this. So, I can write this down as, I can put a b factor here, sine beta by beta, where beta is equal to alpha b by 2, where beta is equal to alpha b by 2. And let me write down what is. So, we obtain a of p y as 1 over under root of 2 pi h cross 1 over under root of b times b sin beta by beta. So, this becomes equal to some constant in front, b by 2 pi h cross sin beta by beta. And what is beta? Beta is equal to alpha b by 2. If you may recall that alpha was equal to p y by h cross. So, this becomes alpha p y b by 2 h cross. H cross is h over 2 pi. So, that is alpha, sorry. Alpha is equal to p y by h cross. So, alpha is equal to p y by h cross, there is a factor 2 here. So, the 2 cancel out, and what is p y? If you see this, if the electron gets moving in this direction, and if this angle, which is the angle of diffraction, is theta, and this is the y direction, then p y is equal to p sin theta. So, you will have p y is equal to p sin theta, pi will come above, and then h multiplied by b. H by p is lambda. So, you obtain pi b sin theta by lambda, pi b sin theta by lambda. So, the probability distribution function will be proportional to, that is, probability of the momentum lying between p y and d p y will be equal to mod a p y square d p y, and that will be proportional to sine square, some constant, sine square beta by beta square, where beta is equal to pi b sin theta by lambda. And this is my single slit diffraction pattern. This is the single slit diffraction pattern. So, how do I explain the diffraction phenomenon? As soon as I constrict the electron, so the slit itself imparts a momentum in the y direction, and the probability of the momentum being lying between p y and p y plus d p y will be proportional to sine square beta by beta square, and that is the single slit diffraction experiment. So, if I show you to conclude this lecture, so I have the single slit diffraction experiment in which you have a Gaussian wave packet in the x direction, and in the y direction you have a single slit. So, therefore, the probability of the momentum, x component of the momentum lying between px and px plus dpx is given by a Gaussian function. On the other hand, if I want to find out the probability distribution function for py, then I integrate this and I obtain sin beta by beta. So, that the probability of the y component of the momentum lying between py and py plus dpy will be proportional to the sin square beta by beta square into dpy. So, that as soon as you constrict the particle to pass through the slit itself imparts a momentum and you obtain this single slit diffraction experiment. Where an individual electron will lie, I cannot predict. I can only predict a probability distribution function. So, that if the experiment was carried out with a large number of electrons, the single slit diffraction pattern will be observed. So, therefore, I have a source of electrons, protons, neutrons, alpha particles or anything that you can think of. It is I describe this as a Gaussian wave packet propagating in the x direction, and then I constrict it within a distance of the order of b to obtain the single slit diffraction pattern. Where an individual electron or the proton will land up, no one can predict. One can only predict a probability distribution, and therefore, that probability distribution is the same as the single slit diffraction pattern, as you must have read in your undergraduate optics course. We will continue from this point onwards in my next lecture. Thank you.